subtopic 16.4, rate of energy transfer by sinusoidal wave on a string. Let's consider this figure. We are going to analyze a proof or example of how the wave going to transfer the energy to surrounding. Okay, so let's say we have a stretch string here, and then this is our hand. Let's say this is the source of our wave. We are going to make a pulse. Okay, we're going to shake the end of the rope or string. So the pulse going to travel, okay, throughout the string. Okay, one section of the string we tie up to a block with mass m. Okay, what will happen to the block? Okay, we are going to observe that the block going to move up, okay, while the wave is traveling or passing through. The pulse is passing through the section where it is tied to m block. Okay, whenever the block is moving up, okay, or there is a vertical displacement from its initial position, it means that the block already has increasing of the gravitational potential energy, okay, because the y displacement just now, right? So this is how the wave, the pulse, okay, transfer its energy to the surrounding, right? So now let's consider another situation for this diagram. Okay, let's say we have a string and then we have oscillator at the end of it. All right, so the oscillator going to vibrate up and down, producing pulses, okay, throughout the stretch string. Let's consider a small part of m within the string or rope itself. Okay, so we know that, okay, this section going to experience velocity and also going to experience kinetic energy, means it's also experience potential energy because it's going to move up and down, right? So in terms of kinetic energy, firstly, we know it's equivalent to half mv squared, and we are talking about small portion of m, therefore this kinetic energy also small portion of it, okay, and then it's equivalent to half dm vy squared. Why is it vy? Because, okay, the motion of this part is up and down, right? And mass is equivalent, also can be replaced with mu x, okay, because mu is equivalent to m over x, which is mu is linear mass density, m is the mass, x is the length of it, right? So substituting the dm here with mu dx, okay, you will get this formula, right? So the one that is constant is mu and vy squared. Dx is supposed to be the one that changes, so we put it at the back. So now we are going to substitute vy with the velocity for wave equation. So this is your vy here, okay, then you're going to do the square for it, dx. So you will get omega squared a squared cos squared kx minus omega t dx, and at t equivalent to 0, okay, the omega t will be 0. Why is it t equivalent to 0? This is initial condition, right? So now your dk is equivalent to half mu omega squared a squared cos squared kx dx. All right, so okay, this is a small element or amount of kinetic energy. If we are talking about for one complete lambda, okay, of movement, all right, so the kinetic energy should be total up. How to total up? We are going to use integration. So integration of decay function with the limit of from 0 up to 1 lambda or wavelength. All right, so you're going to integrate the whole bar of this function to the respect of x from 0 up to 1 lambda. So half omega mu omega squared a squared are constant, so put it outside. The one that you're going to integrate is actually cos square kx, and then integrating this one, you will get this value. We want to integrate the x because we are integrating this to the respect of x, right? So integrating x, okay, we'll get half x, okay, but it's sub to cos squared. So you have to integrate the cos squared. Integrating the cos squared, you will get 1 over 4k sine 2kx. Okay, and then after that, you're going to substitute the limit 0 up to 1 lambda. So you will get this answer. And finally, you will simplify these two parts, become 1 over 4 mu omega squared a squared lambda. This is the kinetic energy just now. Alright. By using the same approach to the kinetic energy just now, we also can show or prove that potential energy for 1 lambda of the wave is equivalent to 1 over 4 mu omega squared a squared lambda. So, E total for within one wavelength must be equivalent to U plus K. 1 over 4 plus 1 over 4, you will get half mu omega squared a squared lambda. Talking about power of the wave, must be the rate of energy transfer. Okay, transfer mechanical wave over the time taken to have it done. So the transfer of mechanical wave just now is in terms of E total within 1 lambda. Time taken within 1 lambda is a period. Okay, then you substitute this one into this and the capital T here. Simplify, then you will get lambda over T here. Okay, can be simplified by using V equivalent to lambda over T. So this one is also can be written as V. Therefore, finally, your power equation of a wave is equivalent to half mu omega squared a squared V. Now, we're going to move to subtopic 16.6, sound wave. Okay. Let's recall that sound wave can be categorized into 3 types or level. Okay, the most common to us is audible wave. Okay, this is the one that really effective and usable for us. Okay, within the audible frequency, which is 16 hertz to 20 kilohertz. Okay, this is the range that we as human can hear things or sound. Infrasonic wave, which is below than 16 hertz. So infrasonic waves, some certain animals can communicate within this infrasound level. And then third one is ultrasonic wave, which is over 20 kilohertz, which is bigger, much bigger compared to our level. So this one also certain animals can hear or communicate within this range. Right, so if you see here, okay, the lower the frequency, okay, the medium frequency, the highest frequency, if you see here, the shape of the wave is different, right? Why is it so? Because it's the V equivalent to lambda F. If the V is the same, then you have to manipulate this one, right? If let's say the medium of the or the V of the wave is the same, so the lambda and the F will be varied. So as we are now in sound wave, we know that sound most of the time the medium that useful to us is air. Okay, so pressure variation in sound wave that going to be the mechanism or the way of propagation or transfer of the sound within air. Okay, we see this figure. All right, let's say we have air within a pistons, okay, and within a column, and this is a piston. Then this is before the piston is moved, the gas is undisturbed. So now let's say the piston is moved to the right. Now the gas going to be compressed, okay, by the motion of the piston. So this area will experience compression, okay, where, okay, the size or the distance between the neighboring molecules will be decreasing. So compression will be high here, pressure will be high here, and as well as density. When the piston stop, okay, the compressed pulse continue through the gas. So just now it's here, right? Okay, it's going to transfer the pressure to this area and this area right now. So it's just similar to the way of the pulse in a stretch string move. Okay, so if let's say we are going to produce, okay, certain vibration or motion within the piston itself, okay, to the left, to the right, to the left, to the right. So what will happen to the air within the column is going to have a series of pulse, okay, series of pulse, where, okay, it's alternating between compression region, rarefaction region, and compression region and rarefaction region all over again. So similar approach to the pulse or wave string system. Okay, 1 lambda is defined as distance traveled by the same point, let's say from crest to crest, or throw to throw, or crest to crest. Okay, also 1 lambda. Time taken to have 1 lambda is known as period. So S is the position of the small element relative to its equilibrium position. We can express, okay, the S just now, position of the small element, okay, is depending on the X and T, as a function of X and T, whereas it's equivalent to, because it's vibrating, it seems like it's experiencing simple harmonic oscillating as well. So S max cos kx minus omega t. What is S max? Is displacement amplitude. And then the K is the wave number. The omega is angular frequency. Why is it minus? Because it's moving to the right. And we also can have another expression for the variation of the pressure, okay, within the gas, okay, of the air column here. Okay, delta P is equivalent to delta P max sine kx minus omega t. Delta P max is the pressure amplitude. Why is it cos and why is it sin? We will explain this in detail later on. Right. Okay, so if we refer to this diagram, right, just now, okay, before the piston is moved, the gas is undisturbed. Whenever the piston already compressed, okay, there is a compression region experienced by the gas dissection. When the piston stops, okay, the compressed pulse continues through the gas. So this is similar diagram to the previous slide just now. Okay, so what happened actually to the undisturbed gas when the piston is moved? Okay, it's actually happening like this, right? So let's say initially this is the section we are going to consider undisturbed gas, okay, having A area, okay, and delta X, okay, as the distance. Now when the piston is moved to the right, okay, what will happen? Okay, the gas going to be compressed, okay, and slightly displaced, okay, from S1 to S2 right now, right? So in initial, okay, before it is disturbed, okay, volume initial is equivalent to A delta X, right? And then after it is displaced throughout delta S, S1 minus S2, okay, the change in volume is equivalent to A delta S, right? So as we know, the gas right now experience in terms of change in volume, it means that it's involved bulk, modulus. So change in pressure, recall back this one, change in pressure is equivalent to negative bulk modulus change in volume over initial volume. Why is it negative here? If you still remember, to counter back the negative part of this. Okay. So how to have delta V is here, A delta S. How to have V initial is here, A delta X. So from here, you can simplify the equation, become this delta S over delta X. Right? Because this is a very small portion compared to the whole things here, okay, we may also replace the change in here to the partial differentiation, because when we talk about partial differentiation means that we are focusing on a specific region or specific small of time. Right, for this case, a specific region, small region. Right, so ds over dx. Right, what is our x just now? What is our s just now? Is the s max cos kx minus omega t. So what are we going to do? We are going to differentiate the whole function here of s to the respect of x. Right, so means that we are going to differentiate the cos function, where it gives us, okay, so we have here b as max k sin kx minus omega t. So delta p max, if we're talking about maximum of this, okay, must be this function going to be maximum as well. Maximum value for sin function or cos function must be equivalent to 1. So if this part become 1 for delta p max, it means that bs max k sin kx minus omega t. So the whole function here must equivalent to 1. That is how we have this. Right, bs max k. The final equation here is the one that important to you. Then okay, we have, in summary, we have two kind of equation. For the s, okay, small position of the element at as a function of x and t is equivalent to s max cos kx minus omega t. Why is it cos? Because at x equivalent to 0, at t x equivalent to 0, because at x equivalent to 0, the s already at s maximum. That is why the function is cos, right, which is correlate to this, right? Okay, then delta p is bs max k sin kx minus omega t. So why is it sin? Okay, if you see here, at x equivalent to 0, okay, there is no pressure exists yet. Okay, so no delta p. At x equivalent to 1/4 of the lambda, okay, or at this position, at x equivalent to this, okay, the pressure is maximum, okay, and whereas, okay, the object, the material, the gas, the molecule of the gas is fixed here, almost cannot vibrate, cannot have displacement of s. So x is 0 whenever p is maximum, right? Whenever p is 0, again p is 0, s for the molecule of the air will be maximum again, but in negative direction. Okay, that is why for s is the position of or displacement for the gas element is in terms of cos function. However, when we talk about delta p, is in sin function, it's opposite. Okay, speed of sound of wave. Okay, again, we are going to analyze the same part, but even in detail, more detail. All right, so here there is a force applied, okay, from the piston to the undisturbed gas here. So this is actually F applied in terms of X, right, along X. Okay, how come? If you still remember, P is defined as F over A. So to have F, it's P times A. But not to forget, okay, the M molecule within the F column itself, okay, going to give another pressure in opposite direction, right? And let's say now we are going to increase our force, right? We are going to increase our force, therefore the piston going to move, right? So what will happen to our F here is P plus delta P times A. So we have a new force here, all right? Mass equivalent to the displacement produced or occurs, okay, and the distance within this section is V delta T, that give you the X. Right, and now when it's already moved to the right slightly, okay, what will happen? The distance traveled by this section just now, right, is equivalent to Vx delta T. All the time, this pressure also exists, force coming from the air molecule from this part, right? All right, by having changes in velocity, actually we are going to have change in terms of momentum, right? So change in momentum producing also known as impulse, and impulse itself is equivalent to F delta T. And what is our F is delta P and times A. This is our F coming from P equivalent to F over A, right? And then after that, substituting this information, because we have delta P here, delta P in terms of bulk modulus, change in pressure is equivalent to negative of bulk modulus, delta V over V initial. What is our delta V? Negative Vx A delta T over V initial is VA delta T. And then you can simplify this equation, you are left with this. Okay, so impulse just now, okay, is equivalent to A times B Vy Vx over V delta T along I or X component. And we know that delta P is equivalent to M delta V. Okay, so PV initial times with the Vx along I minus 0, because we are talking about change in. Then is equivalent to rho V Vx, okay, A delta T. So this one along I, okay, or X component, right, which is equivalent to AB Vx over V times delta T. So this equation actually can be simplified by substituting, okay, the previous equation that we have in our hand. So from that, okay, we can have V is equivalent to square root of bulk modulus over rho, which is the density. And not to forget that for stretch string, okay, V also equivalent to square root T over mu, tension in the string over linear mass density. This is bulk modulus over linear density, or simply known as density. Right. So in general, okay, the V, the speed of wave, okay, is equivalent to square root of elastic property over inertial property of the system. So if we're talking about stretch string just now, okay, the elastic property is the tension within the string. The inertial property is the mu, okay, the bigger the mu, the harder for us to change the velocity, to stretch the string, and etc. We're talking about gas, okay, then the elastic properties is in terms of bulk modulus, because within the bulk modulus, it talk about changes in volume. That is the elastic property for gas. And the initial property is density of the gas itself. So if we refer to this table, speed of sound in various medium, okay, for example, this section for gases, this is for liquid, and here for solid. Actually, sound travel through all these mediums. However, the one that really useful and understandable by us as human is within the gases. Okay, and since we are talking about the speed of sound wave in the gases, so as we know, the molecule of the gas is very sensitive to the changes of the temperature of its surrounding. So temperature going to vary the most of the speed within gas is equivalent to 331 square root 1 plus T in Celsius over 273. And 331 is actually speed of sound whenever the temperature is 0 degree. Right. And then the T here must be in Celsius unit. Alright. And then you substitute the T, you will get the V of the sound wave within the air having this T of temperature. For example, at 20 degrees Celsius, okay, the speed of wave is 343 meter per second. And also, not to forget about our delta P just now. Delta P max is equivalent to Bs max K. What is our B? Rho V squared S max. The K is omega over V. That is how you get rho V omega S maximum. Okay. Intensity of sound wave, okay, we know that power is equivalent to F dot V, alright, and if we refer to this diagram, okay, again, okay, the same diagram to the previous slide, where we have undisturbed gas, and now we disturb the gas by applying certain amount of force to the pistons, okay, and it's going to move to the right by the distance of x, okay. And we know that power is equivalent to power itself dot, okay. Power times A is the F. This is actually your F dot. Your F dot your x ds over dt is actually V, because it's ds over dt. Okay, so let's madam put it like this. Okay, and then here is actually this one. So now, okay, we can rearrange and or substitute firstly, and now substitute the delta P as a function of x and t times A, and which is equivalent to this sin kx minus omega t, and your s is s max cos kx minus omega t. You're going to differentiate it to the respect of time to have v, and then okay, when you differentiate cos function, you will get sin function, right? So omega s max sin kx minus omega t. Then you may now process the whole part, because this is sin, so you're going to have sin squared, isn't it?